Hello, welcome to my third lab. So we're going to be talking about some key concepts. First, understanding what a circuit is. Essentially, it's just a difference, a potential difference of charge that is going to be equaling to zero in a loop. And you are going to have a flow of electrons because of a capacitor, because of a battery. Either way, a difference in charge at some point in the wire is going to lead to movement, but the overall difference is going to be zero for that closed loop. And that's going to fulfill essentially the conservation of energy and the conservation of charge. Same rule applies for nodes where wires connect, and that's important for understanding current, which is going to be more relevant for some of our other setups. However, more significantly for this lab and the kind of questions that we're working with is Ohm's law, V equals IR, voltage equals current times resistance. Specifically, that's for resistors, as well as that understanding capacitance, which is going to be the charge stored on the total charge that can be stored on a disk or that is being stored, divided by the change in voltage. And that's going to be as a function of time because the capacitor charges, and as it does, it essentially accepts less electrons over time. Our goals are to predict the behavior of circuits with resistors in parallel series and with capacitors, comparing predicted and experimental values and using Ohm stuff. The findings were that the current was closely to what was predicted, essentially 20 milliamps, as well as that the sum of the potential difference is zero, which is again predicted. Lines up a lot. The batteries and the resistors might be inaccurate, but physical laws dictate that they work together the same way as everything else, and then greater resistance leads to a lesser current. So for the first series, you got two batteries, two multimeters, which we're going to use as voltmeters and ammeters, and then negligible resistance in the wire. From both, you're going to observe close to that 20 milliamp value. Reversing the tool, you're going to get a negative value, which makes sense because it's essentially measuring the flow of electrons, which will be going the opposite way. Again, changing to a voltmeter, you're going to see a difference of about 2.6 volts. And the battery should be representing 3, and this just shows a problem with the batteries in this observation, but this is consistent with later numbers. However, when you do that, you essentially open up the circuit. It no longer flows, and so there's no longer any flow of electrons in the circuit. Recording the potential difference by each element. The ammeters have a little bit of a change in the voltage. The batteries add some voltage, and then the two resistors take away their own respective amounts. However, they sum up to zero, which we would predict because of that loop rule. The ammeters across this 100 ohm resistor in parallel have a much higher current. And this makes sense because in parallel, these lower resistance ammeters give the electrons a path to travel outside of the 100 ohm resistor, and therefore it would increase that current significantly. The resistance of the components you can calculate by that change in voltage, as well as with that current that we observed in part 1, and it's pretty close to what we would expect. The multimeters have a small resistance. The 100 ohm actually has an 89 ohm resistance. The 47 ohm resistor has essentially a 38 ohm resistance. You can see here the voltage increases with the batteries and then decreases in each of the resistors. When you attach the voltmeter, you alter the circuit. Why doesn't the ammeter reading change? The ammeter reading doesn't change because the ammeter is essentially acting as a non-resistance part of the circuit. It's just a wire. It's just observing the actual current flow. In the second setup, you are going to have a capacitor, and that's pretty much the only thing that changes. We're going to add a resistor. The resistor is not going to be that 47 ohm resistor. That's just an example. You're going to be replacing that with a light bulb. The first light bulb has a very high resistance. It lights up immediately when connected to a battery and capacitor, and then dims over 1 minute and 20 seconds. When the battery is removed, the capacitor discharges. Same thing is observed, but slightly slower at 1 minute 15 seconds. The second light bulb, which has a lower resistance, is going to be allowing the capacitor to charge and discharge much more quickly with this 15 and 14 second respectively, and that matches the graph you would expect. Here's us doing the experiment. The observed things really did align with the predicted calculations, but readings were not perfectly consistent across experimental steps, and that's because of the errors. Really, it's impossible to recreate the circuit every time exactly correctly, take measurements with totally isolated electric system that have no change to any of the measuring tools or anything, especially with this old equipment and the batteries being so different than what we are supposed to be working with, or even the light bulbs, stuff like that is going to have some error. Also, imprecise measurements of time. The biggest thing that stands out to me when looking over my data actually is knowing whether or not the recorded amps is correct. This has a lot to do with the units. The units were hard to determine on some of the multimeters at times, and also on the light bulbs, simply because some of the tools in order to see those units were scratched out or hard to read in the moment. And with more time and better equipment, that wouldn't have been the case, but that's just how that goes. Discussion questions. So if you charge a capacitor with no resistor in a circuit, how quickly would it charge ideally versus when there is a resistor in the circuit? Essentially, the theory is that with a resistor, it would have a lower overall current, so it would take more time for the electrons to flow into the capacitor and charge it with the resistor. So let's observe this. Let's observe this prediction. Right here, you have a battery. If we connect the battery and the resistor here, you're going to see it charges up pretty quickly, but also pretty slowly. I'm just going to allow this to quickly discharge. Now, however, what we're going to see is we're going to see how quickly it charges. Ooh, my bad. We're going to see how quickly this will charge if it is allowed to go through here with no resistor. And the answer is extremely quickly, demonstrating that this analysis is essentially correct. Thank you for your time.